So we've already seen the first version of the fundamental theorem of calculus where we viewed the integral as a function and we calculated what the derivative of that function would be. In this case, we're going to see the second version of the fundamental theorem of calculus where we're going to take the integral of a derivative. And this is going to be the version that's going to help us actually evaluate definite integrals without having to go through the entire process of finding the Riemann sum and taking the limit of that Riemann sum. Remember, we saw that was quite painful to actually do by hand. So let's just go ahead and give what the second fundamental theorem of calculus says. So if we let y be f prime be a continuous function on AB, so this is the derivative of some function big F of x, then if we take the definite integral of that derivative, we just get f of b minus f of a. This is also sometimes referred to as the net change theorem, because it's telling you if you integrate over an interval, the only thing that matters is the function difference of the functions at the end point. So as you can see, but even before we go any further, this can be quite useful because if I know that what I'm integrating is a derivative, I can evaluate this definite integral just by plugging in those numbers into whatever the function whose derivative is we're integrating. So this is super useful. It isn't always useful to find, or it isn't always easy to find such an f prime. It's not always even the case that one exists, but when it does, this is super useful. So let's go ahead and go through and sketch a proof of this. It's not particularly hard based on what we've already done. So let's start by defining a function g of x, just like we did in the previous video about the first version of the fundamental theorem of calculus, except for now what we're integrating is the function f prime of t. So if we do this, we know from our first version of the fundamental theorem of calculus, if I take the derivative of g, it's just that inside function evaluated at x, so it's g prime of x is just f prime of x in this case. Now another way to view this is if I take the difference of those, so I bring the f prime of x to the other side, I have g prime of f minus f prime of x is equal to 0. So if we recall from earlier in the course, this tells you that g of x minus f of x must be a constant, because the derivative of a function being 0 gives you that the function's constant. So we can go ahead and say, okay, well, let's let that constant be equal to c, and then just bring the f of x back to the other side. So g of x equals f of x plus c for all values of x between a and b. So you see, we've used really heavily here the first version of the fundamental theorem of calculus to get this. So now, since we have this g of x equals f of x plus c, we can go ahead and plug in the values a and b. So if I plug in a, I get f of a plus c. If I plug in b, I get f of b plus c. But remember, we also have g of x is the integral from a to x of f prime of t dt. So we also have g of a is the integral from a to a of f prime of t dt. Well, since we're integrating from a to a, this is just 0. And if we look at g of b, this is the integral from a to b of f prime of t dt. So that g of b is exactly what we're trying to calculate. So now we can combine all of this. And if we take f of b minus f of a, well, that's f of b plus c minus f of a plus c, because those c's just cancel out. But the reason we write it like that is because we know f of b plus c is g of b, and f of a plus c is g of a. So we really get that f of b minus f of a is g of b minus g of a. And then we saw that g of b is the integral from a to b of f prime of t dt, and g of a is 0. So we end up with exactly what we were trying to show, that big F of b minus big F of a is the integral from a to b of f prime of t dt. So not very hard to prove that since we already have the other version of fundamental theorem of calculus. Okay, so as I said before, we can use this to evaluate the definite integrals from a to b of f of x dx, provided we can find this f prime, or this big F, so that big F prime is little f of x. So this is not easy to do in general, but if we can, then we can use this theorem to evaluate these definite integrals. So we refer to this function big F of x, whose derivative is little f of x, as an antiderivative of f, because it's kind of going the opposite direction. Rather than differentiating little f of x, you're finding something whose derivative is f of x. So unlike differentiation, where we had rules like the product rule, the quotient rule, chain rule, things like that, there aren't set rules for finding antiderivatives. So for the most part, if I give you even a really complicated function, you can use the rules we've developed to actually find the derivative of that. It's not always the case. Sometimes the derivative won't even exist, but in general, those rules allow you to differentiate almost any function that you'll encounter. On the other hand, one can give you a very simple function, and it's not always possible to find an antiderivative for that function. So what we're going to do is we're going to build up a library of functions whose antiderivatives we know, and we'll mostly work with those for the remainder of this course. If you continue on to Calc 2, you'll learn some tricks in there to help you find antiderivatives. Again, not every function has an antiderivative, so it won't work always, but you'll learn some tricks to help you. And using computer software for this can also be quite helpful. So let's try one example just so we see at least one example for how this works. So let's evaluate the integral from 0 to 2 of x cubed plus 1 dx. Now remember, if we did something like this with Riemann sums, we would have to find the sum from, say, j equals 1 to n of j cubed. And we saw before that finding those values of those sums can be a bit brutal. So it would take us some time to actually evaluate this if we want to do it with Riemann sums. So the function we're integrating, little f of x, is x cubed plus 1. So to use the fundamental theorem of calculus, we want to find a big f of x so that its derivative is x cubed plus 1. Like I said, we don't have any techniques for this so far, so we're going to have to just guess and check. So note, if I want something whose derivative is x cubed plus 1, well, one thing, if we want to use power rule here, we would know, well, I need something that's x to the fourth and something that's x to get down to x cubed and 1. So if we try that, though, and we take the derivative, we see that the derivative of x to the fourth plus x is 4x cubed plus 1. So that 4 there out front of the x cubed is causing us a problem because we don't want 4, we want just 1 outside the x cubed. So let's try another guess to try to get rid of that 4. So what if we started by dividing by 1/4 and then times x to the fourth plus x? Now notice when we take the derivative of this, when that 4 comes down from the x to the fourth, it'll cancel the 1/4 and just leave me with x cubed, and then the x just becomes a 1. So this does actually work. So 1/4 x to the fourth plus x is the antiderivative of x cubed plus 1. So that means that the integral from 0 to 2 of x cubed plus 1 dx is the integral from 0 to 2 of f prime of x dx, where f of x is 1/4 x to the fourth plus x. So now if we use the fundamental theorem of calculus, this first line here is just an equality because f prime of x is x cubed plus 1. Then the fundamental theorem of calculus tells me, since I've written that the integrand, the thing we're integrating, as an f prime of x, to evaluate the definite integral, it's just f at one endpoint minus f of the other endpoint. And then we just plug those in to f. So I have 1/4, 2 to the fourth plus 2, minus 1/4, 0 to the fourth plus 0. So that first term is 16 over 4 plus 2, so 4 plus 2. So we just get 6 out of this. And so one thing to note here is just how much less work this is than if we found the Riemann sum and then took the limit of it. So you can look back at the one example we did of that and see how much work it was to do that. And then just notice this is new, so it takes a little getting used to, but it's much less work than what we did with the Riemann sums. So obviously do lots more examples of this to get some practice in class.